All right, great. All right, so back to our regularly scheduled programming. Next in this retrosynthesis algorithm, right, how does the program identify starting materials? It typically does this through some kind of commercial database like the Millipore Sigma database. And then lastly, how does a program rank different routes? We said before, this is typically done through a scoring function. And there are some sort of objective and subjective aspects to how we rank routes, right? Objectively, in this route scoring function, the way Cynthia does this is it assigns a certain number of penalty points for every step in a route. So 20 points per step. So it's going to favor routes that are shorter. And then every step that requires a protected group, it's going to penalize this as well. Obviously, just because protected groups are sort of inelegant and it requires you to put them on and take them off. So it sort of penalized things there. And then there's a really high penalty for any routes that contain sort of conflicts with selectivity or incompatible functional groups. It's going to sort of essentially put those way at the bottom of the list. So those are way deprioritized. Obviously, some other metrics, right, is things like yield, things like step count and cost of materials. These are sort of objective metrics we can use to rank routes. On the other hand, there's sort of a subjective component to this as well, right? I think we as chemists understand that when we look at maybe a few different complementary routes and we're trying to decide which one's the best, there's sort of an intuition component to this. We might look at a key step and say, I think that might work for this reason. I have a hunch that the sterics here will be kind of challenging. There's kind of aspects to this that you might only learn if you drew it out on a piece of paper or built a model and kind of studied it that way. Computers can't really do that as well. So some of these subtle physical considerations that we might intuit when looking at a three-dimensional structure are kind of lost on a computer. Other subjective components, there's sort of things that are academically interesting, right? We sort of place a premium on things that are cool and steps that are, really sort of interesting or include cascades, and computers aren't going to be as attuned to that value. There are strategic considerations too, right? We've talked about some of those as well. Okay, so now I want to move into sort of the last section of the talk here, and sort of highlight how computers can be used for the validation, execution, and sort of optimization stage of synthesis planning. So we all probably know, right, once we have a route decided, we have our sort of hypothesis of we're going to make this complex molecule in the following way. We have to go actually do it in the laboratory. And I think while we maybe take for granted that, typically we're using our own two hands to do this, that isn't necessarily true in the computer world. And so people have sort of turned to things like robotics as a really interesting way to automate even the execution phase of laboratory synthesis. So I want to highlight this, I think, really fascinating paper. It came out in Science a couple of years ago from Connor Coley and Klaus Jensen and Tim Jameson, who you might know. They did a collaboration where essentially they married the AskCause retrosynthesis planning program with sort of microfluidics and robotics to sort of automate end-to-end the whole reaction planning, generation of routes and execution workflow. So yeah, like I said, this is sort of involving route selection and AskCause is sort of the brains here. It sort of develops these different reagents and develops the different reactions that are possible. And then the robot actually carries this out in the laboratory. So there's sort of a nice video here. Let's see if I can get it to play, but in their SI, they sort of show in this particular flow synthesis of lidocaine, you can see this robot kind of selecting these different flow modules. Each of these is kind of like a flask, right? So if you have a multi-step synthesis, you need a different flask for every step, and it's sort of aligning these all in a flow setup automatically. And these are routes that were suggested by AskCause, and the reagents were sort of developed by the computer program, which I think is just really interesting. And here you can just see the robot also just sort of picking one by one these different reagents to go into the flask, and sort of it can automate the whole process. So yeah, kind of neat. Computers can do synthesis with robots. I think that's pretty interesting. Okay, so Next, I want to talk about reaction prediction. This is, I think, a really interesting area of the field, a really useful one too. If you think about what a reaction prediction algorithm can do for a synthetic chemist, imagine you come up with a route and you have a key step and you want to know, will this reaction work, right? How can I de-risk my endeavors in the laboratory so that I don't end up getting to the key step and find out that it doesn't work and have to like scrap the project or try a different step? How do we virtually screen ahead of time whether a reaction will work or not? Sort of a holy grail, I think, problem in the field. And there's three different, I think, categories of approaches towards this reaction prediction program. The first is these rule-based approaches, which we've talked a little bit about already. They're just sort of like reaction flashcards, right? They're generally pretty fast, and they're analogous to sort of how humans think about reactions. You know, if we teach a computer an amide bond forming step, it's going to sort of start to predict, okay, if we have an acid chloride in the presence of an amine, we'll probably make an amide bond. That's typically how this works. One downside is it requires manual implementation of these rules. And so it's not very scalable for, you know, really large data sets. And another downside is that it sort of, because it only sort of keeps track of the net transformation of reactants to products, it's sort of ignoring individual mechanistic steps along the way. Sometimes we know, right, if we're trying to evaluate whether some key step is going to work, we can sort of dial into a potential mechanism and say, okay, maybe this step of the mechanism might be problematic because it's sterically hindered, or because, you know, this bond might be cleaved. But these rule-based approaches are sort of going to be at a high level. They might ignore those subtleties. One solution to that issue is to approach it with quantum mechanical methods, like with DFT, where you can really start to look under the hood of a reaction mechanism and start to sort of enumerate different reaction barriers or transition states, and even sometimes quantitatively predict what, you know, product distributions might look like through these theoretically much more accurate methods. As we know, DFT, unfortunately, though, is pretty computationally expensive. And because it's, I think the results that you get can be so dependent on a lot of the assumptions that you make as the user, and because these outcomes can be very context dependent, I think, you know, it remains to be seen whether DFT can truly be used as a sort of wholly predictive tool when trying to decide if a reaction will work or not. But nevertheless, it gives us a little bit more insight, I think, under the hood for, you know, some of these subtleties. And then finally, what you might have seen coming is that there's, you know, also machine learning approaches as well. These are fast and pretty scalable, I think, when you apply them to really large data sets. And they're much less computationally expensive than, say, DFT. One downside, though, is it requires really large data sets to train a machine learning algorithm. When I say large, I don't just mean like, I don't know, hundreds of reactions, which we as chemists might do when trying to optimize something. By large, I mean like 10 to the fourth to even like, you know, hundreds of millions of different data points to try to train a machine learning algorithm effectively. And not only do you need a lot of data, the data needs to be high quality. The data set needs to be clean. It might come as no surprise that in the existing chemical literature, the data that's out there isn't very good. There's a lot of bad data out in the literature. And part of this is just because the data sets are incomplete. We as chemists tend to not show negative results, right? Things that don't work aren't as publishable as things that do work. So if you try to train a machine learning algorithm on what's out there in the literature, it's not going to have a good sense of the things that have been tried that failed. It's only going to know the things that tried that worked. And a lot of data sets are sort of incomplete. And so that can be a challenge. One solution that's been proposed, and people use this quite frequently for trying to generate clean data sets, is to use high throughput experimentation, where if you have a robot essentially do lots of small scale reactions, you can then systematically generate a clean data set, which you can use for training an ML. Okay, so one example I want to highlight in the realm of reaction prediction that's particularly relevant to complex molecule synthesis is this paper from Tim Newhouse and coworkers just this last year. You'll notice that most of the references in this talk are from the last couple of years, which just shows how fast this field is moving. People are starting to use these computational tools in their research more and more. And so if you sort of follow this field going forward, you'll see a lot of growth in the publications as well. But here's this preprint. It's still up on the archive. And what the Newhouse group had an interest in doing is they wanted to make this tricyclic compound, clovane 2,9-dione. And they thought that, okay, well, radical cyclizations are really useful for making these types of rings, but there are lots of different modes of reactivity of these radical cyclizations. So in trying to design a retrosynthesis, right, where do we want to make the disconnection for radical cyclization in this compound? And there are lots of different possibilities for that here. And specifically, as it relates to radical cyclizations, Baldwin's rules are really sort of instructive for trying to predict whether a radical will react in a endo or exo fashion. So here's this classic 6-endo trig, 5-exo trig selectivity problem. And they wanted to sort of figure out, how do we predict the outcome before we actually go and try to make this in the laboratory and spend all of our time trying to evaluate this problem? You can even imagine too, like, what other like modifications to our structure might be required in order to get this to work. We've all probably been there in the laboratory as well. We need our key step, and it only works if there is a TBS group on this alcohol, or it only works if there's unsaturation in this position. And so they wanted to be able to sort of pre-screen a lot of these possibilities before they tried this in the lab. Of course, if you just apply Baldwin's rules as sort of a reaction template, you'll know that generally the 5-exo trig is going to be favored over the 6-endo trig, just as a rule. But we know from the chemical literature that that's not always true. Sometimes you get mixtures. Sometimes the 6-endo trig is favored for really subtle reasons. And so what they did is, they wanted to sort of investigate this possibility further. And they computed a sort of DFT landscape for this particular cyclization, exploring the reaction barriers and the product energies of the 6-endo versus the 5-exo versus the 6-endo trig cyclization products. And what may be unsurprising is that the 5-exo trig has a lower transition state, as Baldwin's rules say, but it's also an endergonic process, right? It's higher energy than the starting material. And so they started to wonder, like, well, depending on how much energy the system has, right, maybe it's not so straightforward to just use this reaction landscape or use this energy diagram to sort of predict what the outcome will be if we run this reaction. If this is sort of the thermodynamic product, but this is sort of the kinetic product, it's sort of a hard call to make that judgment. And so they turned to machine learning as an alternative to sort of the traditional DFT way to predict some of these outcomes. And they used the following workflow. They started with sourcing all of these literature examples from the Reaxys database. So they found, I think, a couple hundred, which is a small data set, but they still worked with it. A couple hundred examples of 5-exo trig versus 6-endo trig cyclizations. They then applied DFT to sort of calculate chemical descriptors on those reactants and products to sort of give a machine learning model a sense of all of the different chemical features and subtleties of each compound. And then from that data, they trained a machine learning algorithm to sort of learn sort of some of the chemical subtleties of these transformations in the hopes that it can predict yield from a given set of reactants. And so that was sort of the goal of what they tried to train this on. There are a bunch of yields associated with each reaction, and so you can train the machine learning algorithm on that data set. From that data set, they thought, or from that trained model, they thought, okay, we can use this to pre-screen our human-generated routes and help us decide which of these key steps will work and which ones won't. And then from that prioritization, let's actually go and try this in the laboratory and see how well this works. And so first, from this data set, they explored a bunch of different machine learning models. I won't really get into some of the subtleties of, what assumptions are built into each of these machine learning models, but this is just to say that they tried a few of them and found one which seemed to work reasonably well, this sort of neural network approach. And so once they had this model in hand, they then started to apply this by pre-screening all of these possible precursors and sort of predicting what the yield might be. So here you can sort of see that, okay, this disconnection is predicted to have about a 46% yield if we tried to run this in the lab. And then they sort of enumerated all of the structural modifications you might make to this along the way in trying to optimize that process. So once they decided that, okay, this seems to have a fair shot according to our machine learning model, they went ahead and they prepared these compounds in the laboratory. I'll just sort of briefly highlight the synthesis here. They started with this cyclopentanone 18, and then did a vinyl cuprate addition, followed by trapping with formaldehyde to give compound 19. This compound was then subjected to Robinson annulation conditions to give this cyclohexenone 20, and then palladium-mediated hydrosilation gives this 21. This is then treated with phenylselenoyl chloride to give this alpha-selenyl cyclohexanone 22, which is set up really nicely for these reductive radical initiation conditions, where the radical is then generated at this position and then reacts with this olefin. And really nicely, I think they found that the experimental yield of this transformation for the 6-endotrig cyclization, which was desired in this case, was really closely matched to what the predicted yield would be. And while this is only one example, and they show a few others as well, I think it's a really interesting sort of example of how one might use these sort of computational techniques and machine learning in particular to help us sort of predict the likelihood of success of some of these transformations before we actually go and carry them out in the laboratory. All right, so the last example I want to talk about today in the few minutes I have left is this really nice paper from the Doyle lab in 2020, where they try to approach the problem of reaction optimization from sort of a new computational perspective. And we're all sort of probably familiar with the classic challenge of optimizing any reaction in the lab, especially for transition metal mediated reactions. There are a lot of variables you can change. So the reaction space is really large. You can change things like ligand, you can change things like base, solvent, temperature. And if you really were to kind of calculate how large this parameter space is, it can be, an exponentially large number of sort of configuration of variables. And the way that this problem has typically been approached through computational techniques in the past, right, when we try to optimize a reaction, sometimes it's worth our time to go through the effort of mechanistic studies, or if we understand what is perhaps the selectivity determining transition state, we can then rationally design a sort of catalytic system that maybe favors one product over another. Another way that this has been approached is something called design of experiments. This technique is used a lot in industry to help kind of find the optimal balance of maybe time, temperature, and concentration, these sort of continuous variables, which can be varied in a very systematic way. And with the fewest number of experiments, you can kind of optimize with just those variables in mind. The last area is sort of a brute force approach. You can do something called high throughput experimentation, right? Where if we just have a robot do thousands of small scale reactions, we can empirically determine what the optimal outcome is just by checking the yields or the GC traces. And so what the Doyle lab wanted to do is to apply something called Bayesian optimization to this problem of reaction optimization. And what Bayesian optimization does is it essentially is a machine learning algorithm that learns how to balance optimization of the reaction landscape with uncertainty of trying to gain the most information possible to sort of train and retrain the model. And so what you first need to do is to generate a large data set, a clean data set of reactions associated with particular yields. This is what they use to train their machine learning model. So in this case, they did an HDE campaign of about 4,000 different experiments to explore this Suzuki cross-coupling between these types of heterocycles. And then they enumerated all of the different yields here. And the way Bayesian reaction optimization works is it uses something called an acquisition function, which helps guide the algorithm for exploring parameter space. So what you typically do, as you might in the laboratory, right, is you just try some condition. And then you have to decide, well, okay, based on my result, what sort of things should I vary to try to get a sense for, the yields in this parameter space. So something called a pure exploitation acquisition function might just favor trying to find the nearest maximum and optimize accordingly. Or something that's more exploration based might prioritize sort of uncertainty and trying to basically find, okay, what is the most different kind of reaction condition that I haven't tried yet? Let's go try that. And then let's go explore over here because I don't know this space very well. And so you can see sort of in this reaction map here, this is sort of a 2D representation of a sort of multi-dimensional reaction parameter space. They sort of plotted on a 2D, kind of like a map, where each of these clusters is kind of a set of similar reaction conditions. And you start here sort of in this region, and an exploitation acquisition function might just try to optimize to the highest yield in this particular region of space, where an exploration function is going to sort of hop around a lot more sort of promiscuously and sort of test out lots of different possible reaction conditions that are really different from one another. So what they ended up opting for in this paper is something called expected improvement, which is essentially just a hybrid between the two. It's going to try to explore, and it's also going to try to optimize to find the global maximum overall. All right, I'm going to skip this just for the sake of time. So they wanted to apply this to this problem in direct air relation. They generated a large HTE data set, and they varied all kinds of different things like ligand and temperature and solvent. So some of these are continuous variables like temperature, and some of these are discrete variables like base or solvent. And what they did is they then trained this machine learning model to learn how to optimize a reaction really well and sort of test whether this worked. They created kind of an online game where humans, you could go on and sign into this website and basically, play around with how to optimize a reaction, where you can guess reaction conditions. And then as a sort of human user, you can decide, okay, this is the next set of reaction conditions I can try. And you have maybe, 20 different rounds of 5 experiments each to try to like optimize this reaction up to 100%. And they actually found that the algorithm that they trained did really well compared to humans in optimizing a reaction in only a few rounds of experiments. So what they tried to do is, each round you maybe try 5 different data points. And then from that round, you put this back into the algorithm, and then it decides you should try this next 5 data points. And then in only a few rounds get to sort of the optimum. So it's kind of interesting tool that shows that, you can use these computer algorithms to help with problems like reaction optimization. They then applied this to a few other problems beyond just Suzuki cross couplings. I think they did a Mitsunobu reaction or a deoxyfluorination reaction, anything where there's a number of parameters you might change. And the program doesn't know anything about organic chemistry. So it's not using any kind of rational thought of, what is the donor ability of the ligand, or, how hard or soft is the base. It's just doing this purely based on data. And so once you train an algorithm on a data set, it's actually pretty general. It's a pretty interesting problem. Okay, so that's all I have for you today. I hope I've given a little bit of an overview of all of computer-aided synthesis planning. It's a really big field. But my hope was that I was able to sort of highlight how computer tools can plug into every stage of the synthesis planning process, something we're all very familiar with, and sort of give a little bit of a flavor of how these might be useful to you in your own research. So I know we're right at time, but I'm happy to stick around and answer questions if folks have them. Otherwise, thanks a lot for your attention today.